received at only one point on Earth at a given instant. Knowing your position on Earth, you can use the Doppler curve to calculate the exact orbit of the satellite. And the reverse is true. If you start with a satellite of known orbit, analysis of the Doppler shift as the satellite passes will tell you exactly where you are anywhere on Earth.
Okay, so if you know the satellite is in an orbit and curving around, and you know it's dropping around the Earth, then you could match it to the ground. The ground would also be dropping around the Earth. But if it were in a circuit, straight, evenly above, doing a circle, then how would we know that? What would give it away? If we were going to not assume that we're on a ball or flat, okay? So the AE map pretty much matches the globe in that the longitudes start getting bigger, the grids start getting bigger the further you deviate from the center or the North Pole up to the equator. So you could get away with it probably to the equator and a little ways past it. But as you got too far south, it would you'd have obvious problems. So what would you have to do to map it on a globe? If it were flat, what would you have to do? Let's think about it. Let's watch.
This fact forms the basis of the Navy navigation satellite system. The system is more accurate than any other navigation system known today. Accuracy that can establish a pinpoint of latitude and longitude. This precision is the result of new techniques for fine control and measurement of time in terms of frequencies generated by ultra-stable oscillators. Of course, there are many astronautical problems that confront this new system. Most of these are the result of the near-Earth orbits used to produce the measurable Doppler effects on which the system depends. For one thing, the satellite does not revolve in a smooth ellipse around Earth. It would if Earth were a perfect sphere with uniform mass distribution. But instead, Earth has various bulges and unequal concentrations of mass.
Oh my God. Look at that. Shout out to Neil deGrasse Tyson for a pear-shaped Earth. Okay, so what would you have to do if it were flat and you wanted to put it on a ball and you truly thought it was a ball? So you would have to, or surveying for that matter, you would have to assume, that it's not exactly spherical. You'd have to make the bottom bigger and the top smaller, okay? Because that's what's happening in reality. Not only that, for the surveyors, for it to start shrinking down in the southern hemisphere, you would need, you'd have to do even more. You'd have to enlarge the equator, okay, so it could start shrinking down. So you'd have to add, so they add 20 miles to the circumference of the equator. And there's only one reason I could think of for them to do that, is to make it where it starts getting smaller. And the grids start getting smaller in the southern hemisphere. But not only that, so they're pear-shaping the Earth, and they get some, margin of error from that, and also with that they get to expand the elliptical orbit to make up the other ground that they need for it to even make sense to them. But that is freaking hilarious.
Then, too, the satellite doesn't travel in a perfect vacuum. Another problem is that the satellite radio signals do not travel in a straight line to Earth. They are bent as they pass through the ionosphere, a layer of electrically charged particles that surrounds Earth.
Yeah, sure, they're bent. So not only do they use refraction down here on the ground for their missing curvature, for their missing curvature from satellite signals, they curve the signal. Since the ground ain't curving, they curve the signal mathematically to give them curvature for the satellite signals. And also, what happened to space-time, time dilation? That's another one of the ways they correct it. But if it were only space-time, and they have the mathematical equations for that. Why would they have to do 2 updates every day for every satellite? If it was just time dilation and whatnot, then they could work it out mathematically. So that's another indicator of something else going on.
As for orbital irregularities caused by Earth's uneven shape and off-center distribution of mass, precise tracking of thousands of orbits of system satellites over the past years and analyses of the accumulated data have enabled physicists to compute these irregularities and predict satellite orbits with.
So what they do is they take and they I've been researching this, and every single satellite has a link. Okay, so it links with another satellite, at least one other satellite, and a master command. They all have like a master command. So even if they handed you control over a satellite, then what they see, they have the problems in the southern hemisphere. They have what they call the South Atlantic anomaly, and then they have the South Pacific anomaly, which cover entire continents, okay, where they say they have problems, and that's what they did to solve these problems all in the South. They don't have the problems in the North, but in the, I'm just saying they already have excuses prepackaged in case you get what you would think would be anomalous information.
Tracking station records the Doppler shift of its signals. The tracking station sends the fresh data via the communication center and the operations center to the computer center. The computer center predicts the orbital coordinates which define where the satellite will be each 2 minutes for the next 16 hours. The computer center prepares a message containing these orbital coordinates and sends it to the injection station. From here, the message is injected into the satellite by high-power radio transmission. California, the Navy Astronautics Group operates the navigation satellite system. The headquarters building contains the operations, communications, and computer centers.
So there's a freaking satellite data chain of command. So it's got to go to the communication center, then the freaking command, and then back to the satellite. So they tell the ship where that satellite is. The satellite ain't telling them where it is. That control center is telling the satellite to tell the ship where it is. So I don't know. You make of it what you will.
Despite our best efforts, satellites aren't always the most predictable. Sometimes they just up and reboot, or occasionally they misbehave for some unknown reason. As you might expect, these failures are a pain for scientists. Like, come on, we're trying to explore the universe out here. But if nothing else, we can take comfort in the fact that we at least understand where some of these errors come from. In one 1980s study, engineers made a map of where many anomalies happened for 2 satellites, and they found something really weird. The vast majority of them happened in a region above South America and the Atlantic Ocean.
Look, the vast majority of them happened from the equator down to the tip of South America, damn near. Like, yeah, of course, it's all an anomalous area.
Is known as the South Atlantic Anomaly, and it's one of the most dangerous near-Earth areas of space for satellites and humans. The story of the anomaly starts with the sun. All the time, electrically charged particles from the sun. But most importantly for this story, some of that solar material gets trapped by the magnetic field and contributes to the Van Allen radiation.
This guy sounds like he's giving a bunch of excuses, man. It's hilarious.
Radiation belts, ring-shaped regions around Earth full of very high-energy particles. Despite the name, they're not actually radioactive. Space scientists use the term radiation differently than, say, doctors do. But in general,
scientists use damn near every term different than the rest of us.
Doctors do. But in general, engineers would still like to launch satellites so they never encounter these belts, because those charged particles can pass right through a satellite's computers, causing hiccups known as single-event upsets. The particles can hit a computer chip and change its memory, basically flipping signals from on to off, or vice versa. And that can cause anything from bad data to severe malfunctions or crashes. The problem is, depending on where you want to put your satellite, the radiation belts aren't always easy to avoid, because despite what you...
So what would you have to say if people were reporting, bad data, bad information in the South, And how come none of this shit ever happens in the north? Okay, to me it points toward anomalous, just more anomalies in the south, because the south is bigger, because the earth is flat.
To avoid. Because despite what you might be picturing, they're not perfectly centered around Earth. They're a little skewed. Imagine you're looking down at the North Pole. You can start by picturing the belt as a ring around the Earth's equator. Now, push that ring a little closer to Earth on one side, near North and South America. Then tilt it a bit, so it gets closer to the Earth near South America and a bit further away near North America. On average, that's what the belts actually look like. They're like this
That's hilarious. You know, this guy didn't get the memo that the Earth is pear-shaped, and the satellites do elliptical orbits, which he might have known that, but I don't think he got the memo on the pear-shaped Earth. He hadn't spoke with the Navy or Neil deGrasse Tyson or the pear Earth, potato Earth. Call it what you want. Everything but a ball.
this because Earth's magnetic field is tilted and shifted away from Earth's geographic rotation axis, meaning the magnetic poles don't line up with our geographic ones. Scientists think that's because the magnetic field is generated by Earth's core not rotating exactly the same as the rest of the planet. Because of this, there's a region near South America, stretching from around 15 to 45 degrees south latitude, where the inner radiation belt is unusually close to Earth. Typically, the belt is at least a few thousand kilometers above the surface, but here, it's only about 600 kilometers up. That region is the South Atlantic Anomaly, and there, the inner belt is low enough to affect and damage satellites. Now, it might seem like the obvious solution is to just not launch satellites that pass over South America, but it's not that easy. For one, sometimes we want satellites there, but even when it's not necessary, it's really hard to avoid this region because of how orbits work. Orbits are symmetric around the equator, so if you want a satellite to pass over a certain latitude in the northern hemisphere, it will also have to pass over the same latitude in the southern hemisphere. So if you want your satellite to fly over somewhere specific, like NASA's facility in Maryland at about 40 degrees north, your satellite will also have to pass over 40 degrees south, right through the South Atlantic Anomaly. Because of this, low Earth-orbiting satellites often end up traveling through this spot for a few minutes every day. And as they do, they encounter those high-energy particles and the potential problems that come with them. One way to protect spacecraft from this is to shield them with physical barriers. But since those can get heavy and therefore expensive to launch, we've had to find other workarounds. A common and clever one is to give a satellite multiple computers that can vote. For instance, you might have 3 computers all running exactly the same code, getting exactly the same information. And if at least 2 of them agree on an action, the satellite...
So you got all these multiple computers. I don't know. There's a lot of contradictions when you're researching these satellites. Just pick the ones that stand out for you. And I don't know. These are the ones that stood out for me, but there's several. But you got to subscribe if you want to see all my videos. I usually make a few a week, so I can't keep telling you the name of the channel. Go to it every time a video. I'm making too many of them. Just subscribe, whether you believe all this shit or you want to ridicule it. To see it when it comes out, you got to subscribe. So you know what to do.